Hey everyone, welcome back to the Deep Dive. We're diving into something you all seem really fascinated by, how AI is making those spoken conversations we have with machines,
Yeah.
like way more realistic.
Yeah, more human sounding.
All right,
Right.
totally. And
Right.
today we're focusing on, specifically on Sesame AI's new, it's open source, conversational speech model, CSM.
A lot of you have asked about really understanding how these AI systems work. So we dug into a detailed report that breaks down the CSM, how it's built, and well, this is the fun part, how we might be able to get timing information for each word when it's spoken, and get this, the visual mouth movements, the vizems that match up.
Oh, wow. So we can know exactly when cat is spoken and see a virtual mouth form the shapes to say it. It's like
Exactly.
next level stuff.
Yeah.
So our goal today is to really grasp this cutting edge tech on a deeper level, right?
Right, like really get under the hood.
Okay, so first things first, what exactly is this Sesame AI's CSM?
It's their newest text-to-speech system. And the big deal is it's open source, so anyone can tinker with it,
Yeah.
which is huge for the research community. The thing that makes it stand out is it's this end-to-end multimodal design. So instead of older systems that handled text and audio separately in stages, this uses these things called transformer networks. They're a newer AI approach, and they're able to kind of process the text and the audio together at the same time.
It's mind-blowing how AI is changing so fast. I remember when text-to-speech sounded robotic.
Early, leaps and bounds.
Now it's like talking to a real person, often. And you mentioned something called Llama for language understanding.
Right, it uses a llama-based foundation, similar tech to those big large language models everyone's talking about these days, so it's got that. And then it also uses a specialized audio decoder specifically for something called Mimi audio codes.
Mimi audio codes, I don't think a lot of our listeners have come across that term. What are those exactly?
They were developed by a company called Qtai. Think of them as incredibly compressed audio. Like imagine all that audio information squeezed into a really tiny package. And what's really cool is they hold both the meaning of the words, which we call the semantic information, and the actual sound of them, the acoustic information. It's impressive.
So it's more than just sound waves. It's like capturing the essence of the speech in code.
Yeah, it's like how do you represent that? All that nuance in just a little bit of data. Pretty amazing.
And CSM uses two types of these Mimi code tokens, right?
You got it. So there's the semantic tokens, and those are all about the words, the linguistic, phonetic content. Those aren't tied to any specific speaker. And then you've got the acoustic tokens, which capture all those unique details of a particular voice, how they say things, like their intonations.
So one is the message and the other is how it's delivered.
Exactly. Like I might say hello really flatly, or I might say hello, super excited. And those acoustic tokens capture all that.
I see, I see. And here's something our listeners will find fascinating. CSM actually takes into account the previous dialogue. So it uses that context to make the intonation and the rhythm sound so much more natural.
Yeah, that context awareness is huge. It's not just saying words in isolation, it's reacting, flowing with the conversation. That's what makes it sound so realistic.
It's like it's paying attention and responding like we do.
Yeah.
Okay, so that's CSM in a nutshell. But you mentioned that this focus on naturalness comes with a bit of a trade-off. It doesn't give us precise timing information for individual words the way some older systems did, right?
You're exactly right. That's one of the key takeaways here. Because it's designed to create this smooth, human-like flow of speech, it doesn't really care about precisely labeling where each word begins and ends. It's all about the overall sound.
So if we want to know precisely when the word hello is spoken, CSM isn't going to hand us that on a silver platter.
No, not directly. It's operating at this sub-word level with all these tokens, and that makes directly mapping those to full word timing's pretty difficult. Plus the documentation and the APIs we have available right now, they don't have any built-in timestamp features. It's just not what it was built for.
So we have to get a bit creative then. How do we figure out this word timing stuff?
Well, the report pointed to forced alignment as probably the most promising way to do it.
Forced alignment.
It's actually a pretty clever technique. So you take the audio file that CSM creates, right? And you also take the original text you typed in, and then you use a tool. There are a few out there, but one that's pretty well known is the Montreal Forced Aligner, and it has these acoustic models. And what those models do is they listen to the audio and they look at the words and they try to match up the sounds in the audio to the written words in the text.
So it's like analyzing the audio and saying, okay, this sound here, that's probably the word hello.
Yeah, and not just the word, but the exact start and end times of that word. It's pretty impressive, actually.
So even though CSM doesn't give us the timing directly, we can use these tools to analyze its output and still get that detail. Pretty neat.
Exactly. And the cool thing is, CSM uses standard audio formats, like WAV files, so those tools should play nice with it.
Compatibility is always a good thing. Now, what about those vizems, the visual part of this? I know CSM doesn't just like create those directly.
Yeah, you're right. Vizemes, those mouth movements, it's another level of complexity. So the big question is, how do we get those from CSM? And the report offers a few potential paths we could explore.
Lay it on me.
Okay, so one idea is to analyze those semantic tokens we talked about. Remember, they represent the individual speech sounds like O or ah or E, and those sounds are directly linked to how our mouths move.
Makes sense.
Right, so we might be able to map these semantic tokens to like standard sets of vizems, like a visual dictionary of mouth shapes.
So like if the token says O, the system knows to make a rounded mouth shape.
Exactly, but it might require like some language-specific rules because different languages pronounce things differently, right? Or we might even need to like train a whole separate model to learn those relationships.
AI, training AI, very meta. What else?
Another idea is to really dig into those mimi codes. Remember how we said they hold both the sound and the meaning of the speech? Well, there might be some like hidden connections in that data to how the mouth is moving.
So it's like the code itself might contain clues about the physical action of speaking.
Yeah, like a fingerprint almost. And we could also adapt, some of those existing audio to Visame techniques that are already out there, but
Yeah.
tweak them to work well with how CSM specifically generates audio.
Interesting. So it sounds like figuring out the visame is a bit more, I don't know, a bit more involved right now than getting the precise word timings, right?
It's definitely a bit more of a research challenge at this point, but super fascinating.
The report mentioned something about the frame rate of Mimi audio codes, that it's 12.5 hertz. And, for smooth animations, you typically need something higher, like 30 or even 60 frames per second. So wouldn't we need to increase that rate for visual stuff?
You're absolutely right. We'd need to do some upsampling, figure out ways to like fill in the gaps between those Mimi frames to get a really smooth animation.
That makes sense.
Yeah.
Okay, so to sum it all up for our listeners, the key takeaway is that while Sesame CSM is amazing at creating really natural-sounding speech, getting those precise word timings requires some extra work, like using forced alignment.
Exactly. And to get those vizems, those mouth movements, we need to explore a bit more, figure out the relationship between how CSM works on the inside and that visual information we want.
It really feels like we're just scratching the surface of what's possible, though.
Oh, absolutely. Imagine, like, in the future, we have virtual avatars powered by CSM, and they're talking to us, but their lips are moving perfectly in sync because we've cracked that Vizeme code. That'd be incredible.
Wow. It'd change how we interact with computers completely. So food for thought for all of you listening. How could the ability to perfectly time words and generate those matching lip movements, how could that transform how we use technology? What new applications might this unlock in the fields you're passionate about?
It's a really exciting area to think about.
It is. Thanks for exploring this deep dive with us, everyone. We'll see you next time.
See ya.